on a few things of identities, first of all, and today is the second. So quickly, we learned this about trig. We learned that if the angle sine, cosine, so this is pi over 6, the small angle, pi over 4, the middle angle, and pi over 3, the large angle. We know 1/2, the square root of 3 over 2, the square root of 3 over 2, and we know the square root of 2 over 2, and the square root of 2 over 2. Then we know that sine squared plus cosine squared of the same angle is 1. Yes, we do know that 1 plus tangent squared equals, or alpha, equals secant squared. We know that 1 plus cotangent squared equals cosecant squared. These are all super important identities. And we know those identities for sine alpha plus beta, or minus, cosine alpha plus beta, or minus, and tangent alpha plus beta, or minus. This was sine alpha cosine beta minus sine beta cosine alpha. This was cosine alpha cosine beta, but minus sine alpha sine beta. And this is tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. So this is basically what we know in trig. Okay. Now 7.3 deals with double or half angles. In other words, we are going to look at still trig functions, sine, cosine, tangent, but of double angle or half angle. So here it is. Sine twice alpha, cosine twice alpha, and tangent twice alpha. So far, I only asked you one thing to memorize, which is this. I did not ask anything else, right? And these three numbers, right? And this has to be known, and from here you should be able to determine those. But we proved everything except these three. That's what we did not prove. And basically I said, well, trust me on this and remember those three formulas. Very useful. Okay. Knowing those, you will not have to memorize these. Eventually, you'll probably remember them. How come that I don't have to memorize sine twice alpha? Because sine twice alpha is, can anyone tell us what will that equal to? Not the formula, but what do you see here? What does this say to us? It says sine of,
2 times 8.
right, or if I say I have two $1 bills, I have 1 plus 1. And when I say twice alpha, what do I mean?
Alpha plus alpha.
Exactly. But if I say alpha plus alpha, then from here I will be able to get this in a blink. Because this is alpha and this is alpha. So sine alpha cosine beta plus, sine alpha times sine alpha. Sine alpha cosine alpha plus sine alpha cosine alpha. What will that equal to?
Sine squared alpha cosine.
Careful. Sine alpha cosine alpha plus sine alpha cosine alpha. That's it. Sine alpha cosine alpha. So I don't have to memorize this. What about cosine twice alpha? If I remember cosine alpha plus beta, I know that that will be cosine alpha plus alpha, which means cosine alpha minus sine alpha sine alpha. What would that be? Equal to.
2 cosine alpha minus 2 sine alpha.
But now I have cosine times cosine.
So that was cosine squared.
That is cosine squared alpha.
Cosine squared alpha. Minus.
Yes, because it's alpha plus alpha
And it's minus.
minus sine squared alpha. And if you remember some time ago last week when we discussed this, I said now it depends on what you want to do or what you need. You could change cosine squared into sine squared if you need an expression sine squared, or you could change sine squared into cosine squared if you only need an expression in cosine squared. And we know that these formulas come from here. If I need sine squared, I will move cosine squared to the other side. If I need cosine squared, I will move sine squared to the other side. So there are two other possibilities. So this is cosine twice alpha, but there are also two other possibilities in which I replace cosine squared by 1 minus. So if I want cosine squared is 1 minus sine squared minus sine squared. What will that be?
1 minus 2 sine squared.
Very good. But now assume that I want to get rid of sine squared. If I want to get rid of sine squared, then I have 1 minus cosine squared. So then, careful now, cosine squared minus 1 minus cosine squared. Because I have to distribute negative 1. So if this piece becomes 1 minus cosine squared, I have minus 1 but plus cosine squared.
So 2 cosine squared.
That's it. So you can say that sine twice alpha has only one possible expression, but cosine twice alpha has 3 possible expressions, but they're not different, right? So once I have this, I can determine this. Once I have this, I can determine this.
Yeah.
So basically, this is the main one, and depends on what you need. If you need to have it in sine squared, then you will say 1 minus 2 sine squared. If you needed to have it in cosine squared, then you will say 1 minus 2 cosine squared minus 1. Is that okay? Knowing the formula for tangent alpha plus beta, can anyone give us tangent twice alpha? So these are together. So what is tangent twice alpha? So remember the formula. Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta.
Tangent alpha,
Very good. That's the top.
1 minus tangent squared alpha.
That's it. That's it. So not too bad for the double angle identities or formulas. I would like to practice this for a couple of minutes. On page 514, let's apply these formulas, see how they work. And then we go back to half angles. So 3 through 10, and the page is 514.
We knew 8.
You said 8? Very good. So let's look at problem 8. We have secant x equals 2. We are told x is in the 4th quadrant. And let's see what they want. They want us to find sine twice x, cosine twice x, and tangent twice x. After we solve this problem, I would like to go back to these formulas because I want to draw your attention to something. Okay, so I'm asked to find sine twice x. I know the formula. This is 2 sine x cosine x. So if I don't have sine x and cosine x, I cannot determine anything here. I am given secant x. When I'm given secant x, indirectly I'm given what? That's it. So if secant x equals 2, then cosine x equals
1 over 2.
Thank you. Is this clear? Very good. I do know the angle because it's something over 2, right? Meaning I should not say 3 because it's not even possible. But it could have been 0.7 over 2. But if it's 1/2, I know, right? I know which angle it is. However, I don't care for that. because the angle is in the fourth quadrant. So then I have to say, okay, what is the reference angle and blah, blah, blah. There is no need for that. They're not asking us to find the angle. They're asking us to find sine and cosine of twice x and tangent of twice x. Once I have sine of twice x and cosine of twice x, I don't even have to look at the formula for tangent twice x. It's sine twice x over cosine twice x. Very good. So I know that this is 1/2. But in knowing that that is 1/2, I know what this is, but remember I have to keep in mind that x is in the fourth quadrant.
Wait, what? How did you get to? Oh, okay, you wrote.
So what is sine? For any angle whose cosine is 1/2 in the fourth quadrant. A sine. We want sine, not angle. Negative. Negative square root of 3/2. Very good. If cosine of an angle is 1/2 in the fourth quadrant, there is no discussion that its sine must be negative the square root of 3/2. I don't care what angle it is, not even bother to identify it. But if its cosine of that angle in the fourth quadrant is 1/2, its sine must be the other number. Clear? Okay, perfect. So then I have sine twice x, which is 2 multiplied by negative the square root of 3/2 and multiplied by 1/2. I'm going to multiply and rearrange, and I'm going to skip, and I'm going to say 1. 1 and 1. So this is negative the square root of 3/2. I don't have to use a formula for cosine twice x, because if sine twice x is negative the square root of 3/2, the other one must be 1/2. But I do have a problem. I don't know if it's positive or negative. Because I don't know if x is in the fourth quadrant. Let's discuss that, very important. If x is in the fourth quadrant, it means that it's between 3π/2 and 2π. Let's multiply both sides, all three sides, I should say, by 2. So let's see where the angle twice x is. So 4π and 3π. So so this is 1, 2, 3π, 4π. But I don't know if it's the third quadrant or the fourth quadrant, so I cannot make an assessment for this. I know it's going to end up being something with 1/2, but I don't know if it's positive or negative. Because if it ends in the third quadrant, it will be negative. If it ends in the fourth quadrant, it will be positive. So I can make an assessment. So I have to use the formula. And now I do want to use only one of the formula with only one trig function in it. If you go, remember we have 3. 1, 2, 3. I don't want this. I don't want this. I want this because cosine is 1/2. So I don't want to replace both. I don't want to replace this because it has a square root in it. I may forget to square. Who knows? I prefer this because it's 1/2. 1/2 squared is 1/4. So I will write cosine twice x equals 2 cosine squared x minus 1. And I will say 2 times 1/2 squared, which is 1/4 minus 1. And then I simplify. And I see it's negative. So we will end up in the third quadrant if I were to graph 2x, twice x. So 1/2 minus 1 is negative 1/2, which we knew. We knew the answer, but we didn't know the sign. But now I guarantee, and I can say for sure that 2x is an angle between 3π and 3π plus π/2. So 7π/2. Or you can say 2x, that's fine too, in the third quadrant, for sure. Because only in the third quadrant, its sine is negative and its cosine is negative. So it must be in the third quadrant. Now, no questions about tangent. I don't need any formula once I have these two. Tangent twice x is sine twice x, negative the square root of 3 over 2, which I expect to have what sign for tangent? Yes, in the third quadrant. So this is the square root of 3. So this is an application in which we are given some information and we are asked to find sine, cosine, and tangent of twice x. Any questions for me here? Any questions? Is this okay? Anyone? Paul, you have a question?
No, I'm just looking at it.
Okay. Is this clear? Okay. I would like to look at one more problem, but as I mentioned, I would like to go back to the formulas for a minute. So remember a long time ago I said, when you give me a function, let's say x cubed minus 1 over x plus 2, and you ask me, what do you see? This is what I will say. I see f of whatever equals whatever cubed minus 1 over whatever plus 2. This is what I see. This is the pattern of that function. Now, if you ask me, what do you see here? I'm going to say the same thing. I'm going to say sine of this is twice sine of this divided by 2 times cosine of this divided by 2, because that's the pattern I see. Sine of double equals 2 sine of single times cosine single. So now, if you say to me, okay, I got the pattern. I want you to find sine 7x using this formula. I'll say, okay, no problem. 2 sine 7x over 2 cosine 7x over 2. If you say, now find sine 4x, I'll say, fine. 2 sine 2x cosine 2x. If you say find sine x, I say no problem. 2 sine x over 2 cosine x over 2. If you say find sine x over 4, I'll say no problem. 2 sine x over 8 cosine x over 8. And I can continue forever, as long as I understand the pattern. The pattern says sine of a double angle equals to sine of the half angle times cosine of the half angle. And that's all I did in all these examples. Angle, half angle, half angle. 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 So I got this by dividing this by 2, according to the pattern. I got this by dividing this by 2, according to the pattern. So the point I'm making here is that this is not a stationary formula, if you want. It's a dynamic one. You should look into it. You have to look into it and understand what it says. It's an active formula. I can plug in anything I want. Like here, and you can say, of course, except negative 2. And I would have to agree. For this rational function that I gave as an example, I cannot plug in negative 2. But I can plug in, instead of x, x plus h. I can plug in 4x. I can plug in anything, as long as I follow the pattern. The same thing with the formula. And of course, it works for all the other two, right? For the other two. So for example, if I want cosine alpha over 2, I'll say no problem, depending on which of the three you want. So if you want the core one, then I will say cosine squared alpha over 4 minus sine squared alpha over 4. Because the pattern is cosine twice alpha equals cosine squared alpha over 2, twice alpha over 2, and twice alpha over 2. So this angle divided by 2 and this angle divided by 2. And the same thing with tangent. Okay, so why am I talking about this so much? Yes, go ahead. Paul?
Oh, okay. Yeah, I get it.
Better? Okay, so now, why am I saying all this? Because, for example, problems 29 through 34 on page 515 are asking us to identify, for example, this pattern. Cosine squared of 5 theta minus sine squared of 5 theta.
What is that?
I'm sorry, I copied it without telling you. It's 31. It just caught my eye. 31 part B. So it's asking us to reduce this and simplify it or condense it or do something to it. So let's look at it. Because it's cosine, cosine minus sine, sine, I know exactly which identity it refers to. Not to sine, not to tangent, correct? Tangent is a ratio.
What's that?
And sine does not have cosine squared in it.
Right.
So it must be the only one that is cosine. But now the question is what? Cosine of what? So this has to be twice the angle, and this is the angle, and this is the angle. So what could this be?
Tan theta.
That's it. 32 caught my eye, part B. So twice sine theta over 2, cosine theta over 2. This is typical for which formula? We only have 3. I know you say, you can say, you keep saying only 3, but there are already 10 that you talked about. But there are only 3 different patterns. There is the pattern sine, sine. I'm sorry, sine, cosine. There is the pattern cosine, cosine minus sine, sine. And there is the ratio for tangent. So which one is this?
Sine.
Of course. So I know it has to be a sine. But now the question is what angle?
Which number?
32B. You can, I'll let you choose any problem you want right now. But we haven't looked at the half angle yet. That's why I didn't say please choose.
Okay.
Because they are mixed in that set of 29 through 34. So sine what? I didn't hear. Very good. Is that clear? Because that's the pattern. Sine theta equals 2 sine theta divided by 2, cosine theta divided by 2. Okay. So now let's continue with the half angles, half angle identities. Half angle identities. Yes, please.
Question.
Yes.
Keep going. Where did these come from? Like, for example, what is a doubling?
Why?
Yeah.
Okay. Very good question. Do you remember when we looked at sine alpha plus beta and we wrote the formula directly? This one we did not prove. Sine alpha cosine beta plus sine beta cosine alpha. And I gave an example right away, and I said, for example, if I want to determine sine of 75 degrees, exactly, you can say, punch it in, and you're going to get an approximation.
Right.
But if I want it exactly, I will be using cosine 45, I meant to write sine, of course, sine 45 degrees plus 30 degrees, or 30 degrees plus 45 degrees, and I will be using this.
Right.
Okay. Now, what will happen with sine twice alpha? For example, or sine sine alpha over 2, which I'm just getting to, more useful. For example, let's say I want to show that, let's say alpha equals 30 degrees. So I want to show that sine, if alpha is 30 degrees, this will be 2 times 30 degrees, which will be sine 60 degrees, but also 2 sine 30 cosine 30. And I'll show that these are the same. So what is sine 60 degrees? Is the square root of 3 over 2. What is sine 30 degrees? We know it's a small angle, and this is the square root of 3 over 2. Oh yeah, for some reason something disappeared in my eyes. So I get the same thing. This was a simple example because we knew everything, but we may not be able to. We may not know the angle. For example, let's say I want to find sine 15 degrees. Now I have a different way than saying sine 45 minus 30. I have the way of sine 30 degrees divided by 2 for the half angle. And of course, this has to wait because I didn't get to it yet. I'm just doing it right now. So these are formulas that are derived from the original sum and sine of a sum and difference, cosine of the sum and difference, and tangent of the sum and difference, because they have other applications. Furthermore, these applications, these formulas, will be used in trig identities and trig equations. So we may have a trig equation. I'm jumping ahead, but I'm not going to solve it just now. So for example, I may have sine twice x plus cosine twice x equals 0. Let's say equals 1. Doesn't matter. I didn't think of it. I just gave you an example. So how do I solve something like this? Well, I will have to use the formula. I would possibly have to change it into a tangent and divide by both sides. Who knows? What I would have preferred here is what we did last time, and simply multiply and divide by the square root of 2 over 2. Why by the square root of 2 over 2? Or multiply both sides by the square root of 2 over 2. Why? Because there is, yes, because the coefficient in both of them is 1. And I will change this into cosine pi over 4, and in here into sine pi over 4, and then I will condense this. That's the way of solving this particular trig equation, because it has sine and cosine in it. And that makes it difficult. If it has only sine, it's okay. If it has only cosine, it's okay. But once it has both, it's slightly more difficult. If I change it using the formula, it will take longer. And it may be too difficult to solve. Because this is 2 sine x cosine x, and this is, so it has both.
Right.
That's the difficulty. Every time we have more than one trig function in an equation, it becomes more difficult. But we can change it into one trig function to sine. Very good question. Thank you. So now let's look at the half angle identities. So like before, we are really asking ourselves, okay, what if I have this to solve? What if I have this to find something about? Or what if I have this? So this time the angle is half of it. Slightly more difficult, more involving when the angle is half. When the angle is double, I just refer back to the previous formulas and we're done. This is a little bit more difficult. Okay, so before we look at these, I'm going to have to come back to cosine twice alpha. And you can say, I don't see the connection. You will see the connection in a minute. So cosine twice alpha. Can anyone remind us? There are 3 formulas. But I want one that has only sine, and then I will look at the other one that has only cosine.
1 minus 2 sine squared.
Very good. Yes. I would like now to solve for sine squared. So this is my variable now. I want to solve for this. What will I have to do first? Remember what we did in law of cosines? Because I'm solving for this and it has negative, I recommend doing this. It's not a big deal. You can multiply both sides by -1 later. But I think it's a good practice, a good idea to do that. So I have 2 Sine squared alpha equals 1 minus cosine twice alpha. So I moved this term that was negative to the left-hand side, and I moved this term that was positive to the other side. And I'm one step closer to solving for sine squared. What will I have to do now to solve for sine squared? Exactly. Sine squared alpha. In general, I say, do not write a fraction line, right? Now I'm kind of saying, it's better if I write a fraction line on this problem. This particular formula is called reducing powers. Reducing powers formula. In the same way, we will be able to determine cosine squared alpha. Can anyone have an idea? Or we can go back and do it step by step. You don't have to guess. You want to go back and do it step by step? Yes?
I'm trying to. 1 minus 2 sine squared alpha.
Yes, very close, but it will be plus. Yes, let me tell you why it's plus. Because the formula for cosine twice alpha in cosine will be twice cosine squared minus 1. So that's the only difference, indeed. 1 plus cosine twice alpha divided by 2. These are the two formulas for reducing powers. And now the obvious question is, really, what does this really mean? Why would you want to reduce powers? Why? Well, the reason, the question, this question, exactly. Awesome. But why? Why do I prefer that? You have to wait till integrals. So that's the reason. That's the reason why we need to do that. Because when you determine the integral from this, impossible. But since they are the same, the integral from this will be very easy. So these are the formulas for reducing powers. And now you can say, wonderful, but this is what you promised. What's this? Right? Good. So now I would like you to look at this pattern very carefully and give me exactly what I'm after. And of course, cosine squared alpha over 2. So let's start with the first one. Tell me, what should I write? And then you will see the connection. I am ready. Obviously, it has to be 1. Obviously, it has to be minus. Obviously, it has to be a cosine. And obviously, it has to have 2 in the denominator. I need this. That's it. Because we know now how to look at these patterns. And we know what they really say to us. So if this is alpha, obviously the pattern says twice alpha. If this is alpha over 2, this must be twice alpha over 2. Because that's what the formula is telling us. Good. So finally for cosine squared. Yes. That's it. So these are these two. And you can say not so fast. Because this is sine and cosine. And what you have here is sine squared and cosine squared. But we know this pattern from the first steps in algebra a very long time ago. How do I determine sine alpha over 2? What do I need to do to both sides to get sine? Yes? Of course. Right? Of course, that's all I need to do. So then sine alpha over 2 is, can anyone dictate? If I omit something, I'll be in trouble.
Okay, plus or minus.
Thank you.
Would be the
1 minus cosine alpha over 2. And that's this. And now I want cosine alpha over 2. And that would be
plus or minus. Square root of 1 plus cosine alpha.
I would consider these two formulas as important as sine squared plus cosine squared equals 1. They are that useful. Tangent will be the ratio of these two. There is another,
It's weird because it's only cosine.
exactly. Exactly. Because it comes from this formula of cosine twice alpha, which has 3 different presentations, and you can use the one with sine alone or the one with cosine alone. And that's why they involve cosine only.
So there are other versions, I guess.
Nope, not for sine and cosine.
Okay.
Of course, tangent alpha over 2 will be plus or minus this over this with a square root. And I will add here, but I will give them to you if it comes to that. And we can prove them if you want later. Tangent alpha over 2, it has on page 510, at the bottom of the page, 2 more formulas. 1 minus cosine, I'm not requesting you to remember these. I will give them to you in a... So tangent alpha over 2 is 1 minus cosine alpha over sine alpha, or sine alpha over 1 plus cosine alpha. These formulas you don't have to remember. But I'm going to write them for you here. So 1 minus cosine alpha over sine alpha, and sine alpha over 1 plus cosine alpha. This one we need to remember. Okay, now we're ready to practice anything you can think of in